search of our cosmic origins. Located high in the Andes mountain range, the 66 antennas that make up the Atacama Large Millimeter Submillimeter Array, ALMA, are an imposing sight. Under one sky, more than 20 countries embark upon a scientific endeavor that can only be realized through collaboration. North America, Europe, East Asia, and Chile work together to answer humankind's fundamental questions. Northern Chile was chosen as the site for ALMA because the Atacama Desert is the driest in the world. Its atmosphere, almost devoid of water vapor, enables detection of some of the faintest signals from the universe. Over 16,500 feet above sea level and covering distances of up to 10 miles of the Chajnantor Plateau, the ALMA antennas work as a single large telescope. A supercomputer combines and synchronizes all of their signals in real time. Thanks to this engineering and scientific feat, we're learning about the cold universe, the secrets of planet formation, and the chemical elements that constitute the building blocks of life. Professionals from around the world work for ALMA, pushing the limits of knowledge every day. In Chile, about 50 staff members are based in Santiago, while another 200 work in shifts at the Operations Support Facility close to the town of San Pedro de Atacama. Most of the staff works in the offices, laboratories, and antenna control room of this facility at an altitude of 9,500 feet. Others ascend to the Chajnantor Plateau at 16,500 feet to maintain and relocate the antennas, among other tasks. Strict safety protocols are crucial under these conditions. Thanks to leisure and residential facilities, staff can lead a healthy lifestyle, playing sports and games, watching movies, enjoying nutritious meals, and resting in comfort. ALMA plays a key role in global astronomical efforts. Along with other radio telescopes, it allowed the first image of a black hole to be captured. Without ALMA, that goal would have been unattainable. The Chilean astronomical community actively participates in ALMA research and discoveries, using its 10% of observing time. The radio telescope also contributes to workforce development and supports national and regional scientific, technological, and outreach projects. An example of the latter are the thousands of visitors who tour the facilities each year. ALMA respects the local Licanantay or Atacameño indigenous culture, supporting educational and other projects in the town of Toconao and San Pedro de Atacama, preserving archaeological heritage sites, and protecting the unique flora and fauna of the region, to name a few initiatives. Mirroring the antennas that work in unison with one goal, under the same sky, the international collaboration that ALMA embodies continues the search of our cosmic origins.
Hey everyone, welcome to ALMA's virtual tour today. My name is Thais Mandiola. I'm a visitor coordinator at the observatory. Thank you for joining us and having this instance to talk to some of the staff members that will be talking us through about the ALMA software today. Before starting, it's important to clarify, though, that at this moment, and since a year and a half now, no visits are being made to the observatory due to the pandemic. And ALMA is not really 100% operational either, but our interviewees will let us know a little bit more about this and how it's working nowadays. First of all, let me talk about a brief introduction of the subject that we'll be going through this afternoon. So this is the ALMA Common Software, or the provides a software infrastructure common to all partners and consists of a documented collection of common patterns in and of components, which implements those patterns. The heart of the ACS is based on a distributed component model with ACS components implemented as Corva objects in any of the supported programming languages. The teams responsible for the control systems development use ACS components as the basis for control high-level entities and for the implementation of devices such as an antenna control. ACS provides common Corva-based services such as login errors, alarm managements, configurations, database, and lifecycle managements. The ACS is based on experience accumulated with similar projects in the astronomical and the particle accelerator context, and reuses or extends proven concepts and components. Although designed for ALMA, ACS can and is being used in another control systems and distributed softwares projects since is implemented. Proven design patterns use state-of-the-art, really reliable technology. Through the use of the standard construct components, non-ACS developers can easily understand the architecture of the software modules. And this makes maintenance affordable even on a very large project such as ALMA. So we know that this is a complex subject, so we will have this special guest today that let me introduce you to the staff members that are joining us. We have Maria Jesus Lopez, who's a software engineer. We have Tomás Stein and Camilo Saldias joining us. How are you guys? Thank you for being with us today and talking us through about all this information that for me is really Chinese. I really don't understand much. So I will be one of the people that will be understanding more about each part of this software, okay? Hi, Maria Jesus, Tomás, and Camilo.
Hi, Thais. Thank you for having us.
Hi, everyone.
Hello.
So before we start and get into more of the complex theme, it will be interesting that each one of you could tell us about the journey that led you to ALMA. What did you study before getting to work in ALMA? And now what are your functions in ALMA? What are your duties? And you can talk about a little bit of your position in ALMA. Yeah, let's start with you, Maria Jesus, please.
Hi, good afternoon, everybody. I study the computer science in Universidad Católica del Norte in the Antofagasta region. And I work in Observatory ALMA since 2020, before the pandemic started. So we have the pleasure to work on site for a couple of months before the pandemic started. And I work for the support and diagnostic groups where we operate daily to daily the supports and troubleshooting with different teams during the observatory operations.
Great, thank you. And your duties are monitoring the software or letting know any alarm?
We are part of the frontline software support, so
Yeah.
any issue troubleshooting normal operations is going through our group on the software support, and then we manage them with different software teams in the software department or engineering. We will explain a little bit of our labor further on the presentation.
Okay, perfect. And you, Thomas, could you tell us something about you and your journey?
Sure. My journey is long with the ALMA software. I'm also a computer science a professional. I studied at Federico Santa Maria University. I've started working with ALMA as a student. I was invited to a project that was using the ALMA software, the ALMA Common Software, actually, the ACS. And this was in 2007. And at that year, it was part of a project for one of our courses there at the university. And by the end of the year, I was invited to be part of the distributed programming laboratory at the university. They were granted for a funding from ALMA CONICET, so they had 3 years of work with the ACS, and I started working there until 2012 with the ALMA Common Software. At that year, I worked part-time for ISO, developing now the ALMA Common Software. I was a junior engineer for them for these 2 years. And by the end of this 2 years period, I was invited to San Pedro Atacama, to ALMA Observatory, to finish my part-time job in there. And during these 2 months, an opportunity for future work appeared, and I opted to apply for this opportunity. And since then, I've been working at ALMA in 2012. It's been a long time. I mean, I was working almost 7 years, I think it was, doing shifts at ALMA, at the OSF in San Pedro. And after that time, I applied to a new position here, a software development lead, and I moved to Santiago somewhere around the beginning of 2019. And now, as a software development lead, I supervise and coordinate work with the people at our team. And I also do a lot of development for the ALMA Common Software, as it's a responsibility for group these days. And I try to participate as well on the strategic view of our software group.
Perfect. So you now with your new positions, you have to go for the shifts or not really?
I don't have to go as often. I only go for specific missions or tasks, but I don't have to regularly go to the site.
Okay, perfect. Yeah, long journey, great. And Camilo, what about you? Tell us about your journey to ALMA.
Well, my journey isn't as long as Tomas, so it isn't as an interesting story.
So I think Camilo, we lost you.
Oh, there it is, I think.
The connection.
Is it back?
Yeah, now it's back.
Yeah? Okay, good.
Yeah.
I was saying that my journey isn't as long as Tomas. I started my relationship with ALMA about in 2019, beginning 2019, when I started to make my my second internship here at ALMA. And I started to know what they were doing, starting to learn about their culture, what they did, how they worked, and later in the year, it was just pretty much a coincidence that right at that point when I was leaving university, a software position was open in ALMA. So I said, let's just take it, let's just go for it. And I ended up here working at ALMA. What we normally do on the day-to-day here is we just test software. We receive the software that is being delivered from all parts of the world, from North America, from Europe, from East Asia, which are the partners of ALMA. And we do the testing here in Santiago. We unify all the software into one cohesive system. We do all the testing on it. We then basically verify that it actually works, that it does what it's intended to do. And then we hand this software over to the science people so they can actually check out that the software actually makes sense from the scientific point of view. That's more or less what we normally do at the area that I work on inside the software group.
Okay, perfect. Thank you. So I understand that you have a presentation, so we can break down this topic and you can go explaining us what is the ALMA software, how it works, uh, how is it determined with different areas of ALMA. You can talk us through about that. We can start sharing that presentation.
Thank you. I will just do a small introduction here. This presentation was prepared by us three, but also by Victor Gonzalez and Camila Martinez, who will be presenting the Spanish version of this virtual tour. So now, Camilo, I think you can.
Yeah, I begin. Yeah, so we want to start this presentation by giving a more of a grand view of what a modern observatory is today, since there are such complex machines involving lots of many different parts and with many different people in charge. We want to give a more of a holistic view, more of a general view of what a modern observatory works. And I guess the best way to describe an observatory today is just as a big data factory. From one side, you have, which will be our clients, which is the astronomers from the scientific community, and they give us what they want to observe in the way of a scientific proposal. These scientific proposals are then taken by this giant machinery, which is here represented by a big giant metal tube, which takes operational data that we take from the sky with this big antenna that you probably have seen at least once during this past time, and also the entire combined effort of scientists and engineers and technicians to make this all work, and then this whole thing outputs scientific data that we then hand to our client, the astronomer or the scientific community in general, in the hopes that they can bring us amazing science in return. So that is more of the general view, and throughout the presentation we will be digging a little bit deeper into how this data factory works here inside ALMA. We will go as deep as we can, so we won't dazzle you with some technical details, but at the end you will have a pretty good view of how this data factory works here inside ALMA. So we'll go to the next one, please. And it all starts with the submission of these scientific proposals. Now, once a year, ALMA does this calls for what we call calls for proposals, where people from all around the world, scientists from North America, from Europe, from East Asia, Japan, and Korea, and so on, and Latin America, mainly here in Chile, submit their scientific proposals to the observatory, and this includes basically what is the object that they want to observe, why do they want to do that, how much time will they take from the observatory in order to make this observation, and so on and so on. Basically, they describe us what do they want to do with the observatory and why they want to do that. What is the benefit from it? Here in the image, you can see more or less the distribution of where these science proposals come from. As you can see, more of them are concentrated on the three partner regions from ALMA: North America, Europe, and Asia, and a small number is concentrated mainly here in Chile, since we are the host country of ALMA. And on the next slide, we will also talk a little bit about the process of revision of this whole scientific proposals. Unfortunately, time is infinite. Time for us is a finite resource. We only can observe for 24 hours a day, so we need to filter out which scientific proposals can we take, and how many of them can we allocate on a typical observing day in ALMA. Normally, due to the high demand on the for ALMA, about 1 out of 5 proposals will be able to be observed at the end of this proposal review cycle, and this is done by a new system that we've started with, I believe this year or last year, where all the scientific proposals, or most of the scientific proposals, are peer reviewed by other astronomers. So normally, an astronomer submits a proposal and reviews a couple more proposals, and that is how we basically rank all the scientific proposals by the scientific value, and we can do some let's say prioritization on which scientific proposals can we observe with the limited time that we have on the over the course of the year. Now, if we go to the next slide, to do all of this, to do these entire observations, to do the data processing, to do this scientific proposal process, we need a software foundation, and we need a solid software foundation which one can rely on. And for us, this software foundation is called the ALMA Common Software, or ACS, which Thais briefly mentioned before the presentation. Without going into too much detail, the ALMA Common Software is an abstraction layer for the entire ALMA software, or most of the ALMA software that we use here. It is a framework for distributed programming. So we normally run certain software pieces on different machines. So the ALMA Common Software really helped us kind of managing all of this. It also allows multiple programs on different servers to interact with each other reliably. So we don't run the entire ALMA software on a single computer. We have a network of computers that work all together in order to perform the observations, the data processing, the data reduction, the delivery of the data to the astronomers. And the ALMA Common Software provides us with a way to for all the software to interact with each other in a very simple way. And this is, and last but not least, the ALMA Common Software is based on what we call a container structure. So all the software is basically contained on software containers that can interact with each other, that can be stuck on top of each other, and it basically provides us the foundation and the fundamentals on which the entire ALMA software is based on. So most of the software that is used day to day to run the operations right now of the observatory on Northern Chile are run using the ALMA Common Software, and most of the software that Tomás and Maria Jesus will talk later on the presentation. So yeah.
Hi, I will continue with the further analysis of the software we use. So briefly, as Camilo explained, the data first step is to capture data from the sky. That's what the antenna instruments help us to gather those data. But then layers of software have to process and operate this kind of data. We have two ways of operating them. One is through a control command language that we can gather the different objects on the system. And the other one is through GUIs, interfaces for users. A typical observation path that you can see there in the top, you can see the antennas that are operated through the control commands. And then firstly, there's a scheduling software that is where the operators, you can see the operator there that is scheduling the projects that Camilo explained before, that were gathered through the submission and all the polling for the reviewing. Then this has to be scheduling. So we have 365 days in a year, 24 hours, etc. Climatic condition. All those data are input there in the system, so the astronomers and the operators can efficiently put those projects in a queue, so we can observe most of the time of the year. So the scheduling leads to the observance activities, and then the control subsystem that is in the core of the system commands the antennas to move. Without a control system, antennas cannot do anything. They are just in the middle of the desert of Atacama. They don't know where they are standing, so there's all these electronic devices communicates to the control system, and they're prepared to obtain the data. Once the data is captured, it fills through the scientific metadata and goes through data capturer, and then also goes through the correlator. So we have two correlators. In the image you can see one, but there's one a baseline correlator and a compact array correlator from the Japanese colleagues or of the joint ALMA observatory. So there's a lot of different components that is being developed by all our colleagues around the world. So it's a multi-group coordination always. And then the data from the correlator system that store the data in binary archives goes through the raw data and is stored by the binary archive system. And also the control system and the correlator sends data to TELCAL, that is the telescope calibration system. So this all kind of the magic of scientific data goes through telescope calibration software. And the metadata from data capturer goes to a metadata archive database. This is basically XML files and binary files that compose ALMA data. Next slide, please. Once we have all the data stored, there's another part of the data processing software that enables ALMA to quality assure, or is needed a quality assurance process to deliver these data products to the scientific community. And briefly, all this processing, reviewing, and delivery of data consists of a group in the observatory. They're mostly of probably 80% of the data process is being through a pipeline of software that is developed in Docker services that automatically process the data. So in my case, in the software support group, we are in charge of every delivery of the software to when there's the data processing changes of the software, we have to deploy and coordinate with the users to validate the changes for every software release. So the software is an evolution of probably changes that is been evolving according to also the technical capabilities of the observatory. I don't think maybe Tomas can tell us of experience in these 10 years of history of ALMA, the software has been evolving constantly. So every tiny details to process data, quality assurance has been increasing. This enables the data processing group to deliver data 30 days after the data has been captured. So this is pretty efficient to me to deliver a lot of data once it's being collected. In 30 days, the scientific community will have the data with some calibrations, references, image, and in a package like this is your investigation, and it's already through the quality assurance and objects and products, what is called this data products. And so after the data processing is being made and the scientific community has the results, they have the last one. The most important, I think, scientific discovery through 2019 was the black hole image of M86. And ALMA was an important part of the data captured in collaboration with 8 observatories. As you see in the left-hand image, that is the black hole image we all know. But without the participation of APEX, that is also in the Chacnactor Valley of San Pedro de Atacama, and ALMA, collecting different data and collecting them and processing with the rest of the observatory, the full image of the black hole wouldn't be possible as we see it today. So the importance of ALMA and then the position is important to, as the software evolves, we are continue collaborating with it. Thank you. So, Tomas, maybe, or I continue?
Yes,
Okay.
I think you already spoke about data delivery, but all these packages that Maria Jesus was mentioning go to the different regions. And as she said, this is after the quality assurance have passed. So I won't repeat this slide. I was just going to make sure that you understood the complexities of having these ALMA regional centers that are on each of the regions in North America, Europe, and East Asia. Okay, so we have seen that there's a natural flow for any observation unit. I mean, we have seen all the complex subsystems or components that are part of the ALMA software, and we have these observation units going through a flow. This flow puts together all the components and makes us realize that this is a very complex and that we need all these components to work together and in harmony for everything to work. So on top of all the complexity of each of the components, we need them to be working together and reliable to make this whole thing work. It's a very hard thing to do, and we need to be looking for issues at any place in this chain. Okay, but on top of the complexities that the software has, as you can see, the software is, or the observatory delivers to several regions, but it's important to know that our teams are also spread worldwide. So we have what we call, in the case of the software department, in case of computing, we have what we call the integrated computing team. And the integrated computing team is just a team of software engineers and other roles that are spread around the different regions, which are the North American one, the National Radio Astronomy Observatory, the European one, which is the European Southern Observatory, and the Japanese one, which is the National Astronomy of Japan. And on top of that, the Joint ALMA Observatory, which is JAO, is the people that works here at Chile, which is the merge of all the regions in Chile. So in the case of computing, this integrated computing team is headed by one of the representatives from each of the partner sites. Each of the sites develops and maintains different software components. And in the case of JAO, our responsibilities are in the software operations, maintaining the common infrastructure, so AACS that was presented before, and the integration and testing roles. If we see here, we can see that the people at the Joint ALMA Observatory is also complicated chart. Our department, the ALMA Department of Computing, or ADC, is right below the director office and shares this step with all the departments. So with administration, science operations, engineering, healthy, etc., etc. And our department has three areas or three groups: the information technology group, IT, which is in charge of the hardware infrastructure, the networking, and other computer-related stuff. We have the archive pipeline operations, which is in charge of the infrastructure for databases and the cluster for processing data. And on top of that, all the maintenance for the databases and the pipeline operations. And then we have our group, which is the software group, which is at the same time split in three areas: the software operations support, where Maria Jesus works. We have the integration and release management, where Camilo works. And we have the common infrastructure and DevOps, which is basically software development, and it's a team I'm currently leading. And we have several people on each of these areas. So then once we are at the JAO, how does our team collaborate with other teams at ALMA? So we have to collaborate with science operations. We have to troubleshoot issues that happens in operations with the software. We have to implement new features and bug fixes in the software. We have to do deployment and maintenance of productions in applications. We have to test new features and bug fixes before the software goes into production. solve software issues in operations, provide support to non-software users, implement tools in order to improve the activities of the team, coordinate software activities with the other software teams in ICT. With engineering, we have to troubleshoot issues in operations, deploy antennas in software. After a relocation, after an antenna is moved from one path to another, we have to provide support to the engineering team. We have to gather requirements for new hardware or new functionalities, and we have to do a lot of stuff with them. And the main people we work with are the science, operation, and engineering teams, but on a day-to-day basis at the OSF at San Pedro, we usually have to do a lot of stuff. So let me put play here, and this is a small video just showing day-to-day applications that are used by the ALMA staff. And as you will be able to see, there are broad technologies. We have both desktop applications and web pages that are used to fulfill different needs for scientists, engineers, operators, software engineers, and all professionals working at our observatory. I don't know, maybe Camilo or Maria Jesus want to comment something about these tools.
Well, we use for analysis of data. Kibana has been really useful for non-software users, as the data collect every second from logs and events from the observatory is quite huge. So Kibana enabled us to see in a more graphic way and analyze without much knowledge some keywords or events through in time windows, so other users from the ALMA joint group can use it and troubleshoot more easily, gathering this data. That's this is a huge improvement that we had during the last 2 years from the pandemic.
Yeah, I could also mention from my side that we normally have, in order to do our testing without affecting the normal operations, we do have a small testing environment that simulates at least in the best of our abilities what we have in northern Chile. So we do continuous testing of all this new on all of these tools. So in a more controlled environment, so we can break things, we can test things until we break them. We can chat with the software developers in order to iterate some solution if we find some issue with some tools. And this is basically what we do every single day. We test software, we iterate on the software, we talk continuously with the software developers in order to ensure that the software that arrives to the observatory on tomorrow on a production level is as the best quality that we can possibly get.
It's really impressive. You really connect with each department of ALMA and are able to perform the observations and all the connectivity with the antennas up to the high side. Is really impressive how the technology is. And I don't know if you mentioned it in the presentation, but I did it in the introduction. And for my case, my question would be, what is Corba? Could anyone help me? What is Corba?
Yes, I can help you. Well, Corba is what we call middleware. Middleware is just a piece of software that helps you connect two things out, or that is an intermediate piece of software. In this case, Corba is an architecture or a design of a communication for distributed programming. So it's a common language that allows us to connect two computers together, but also to connect two programming languages together. So we can have, for instance, one component here in Santiago programmed with Python or Java, and then you can have a different component at San Pedro, Atacama, programmed in C++, and they can understand each other and interact with each other.
Perfect. And you also are the ones that developed the Corba. You work
no,
on something.
Corba is a technology that is it's actually a specification. This was designed several years ago. I'd say somewhere around 20, maybe a little more. And this spec is implemented by different vendors. And we use the software programmed by these vendors, and we use this as the base for ACS. And ACS constructs on top of Corva this container component model that simplifies and hides all the complexities from Corva, because it's not the most friendly framework to work with Corva.
And what about your work? Is it daytime, nighttime? Do you have shifts like that, like the astronomers? Tell us about that.
I work in day or night shift in the software support group. We try to cover 24 hours of the day of support for troubleshooting during observation or troubleshooting data processing application, any kind of issue that is detected during normal operation or during software releases. It goes through our team of the support and diagnostic group. Then we can ask for help for any other during our shift or day-to-day basis. But in my group we work for shifts. Tomas and maybe Camilo can talk about their experience in their working schedules.
Yeah, go ahead. You want to.
My camera
you
died.
lost
My
Camilo.
camera died. That's that
You
was like, wait a little bit.
Okay.
Let me see. There it is. Okay. So normally our working schedule is a little bit more flexible than Maria Jesus. We normally work on by day, but if we need to at some point in time help the software operation guys on some issue, or if our help is required at some point, we normally jump in at night and still do some work. But we still do have that flexibility of schedule to work basically on the schedule that best works for us.
Okay.
Yeah, on top of what Camilo is saying, we sometimes have to do nighttime on-call support. We don't do shifts regularly. It could be an exception, and it's something that Camilo may have to do on the February shutdown, for instance. But this is based on missions, on specific missions. We don't do shifts, but we have to work at night sometimes. For instance, if there's people are training at Maria Jesus team, or if there's a sick leave or vacations, we have to go and support them on the night on-call support.
So for the time that I was working on site before the pandemic, I remember that there were hours that were delivered to computing for the control room. And I saw you guys entering and taking over the system and just working there. If you can tell us, what were you doing during those hours? If you can tell us a little bit.
Yeah, I can probably talk about a little bit more about that. So there are some points on during the week that the planning people on San Pedro give us the system, the real hardware. I mean, basically the real antennas there at San Pedro, for us to test these new software releases with the real hardware, with the real system, and that basically gives us the opportunity to test all of these new capabilities, all of this new software that they deliver us, using basically the real deal, the real antennas and the real correlators and the real machines and the real everything. Because there are some issues that only appear or that you can only see when you test this software with the real machines. That there are some things that you just can't simulate on a computer environment. You need to have real antennas pointing at the sky, taking data in order for you to discover these issues and to basically test the software as thoroughly as you possibly can.
Okay, perfect. And another question that I have too is about the JITAs. Do you work with that also? Are you part of that? management of the
Yes.
alarm system. I know that it's alarms. Maybe it's more an internal thing, but for people that are looking at us now, it would be interesting to let them know what these alarm systems are. They alarm systems? I don't know.
Yes, there are alarm system that, for example, for the machines that use the system that notify us when memory consumption of this space is running or some application is having troubles. They notify us um, by email or message to take a look immediately we can. As in normal operation, as Camilo explained, in real hardware and real software, is dramatic to have any kind of like a bottleneck that is delaying the observations and the data gathering. So we are continuously checking alarms, as there are several components in the online and offline system that communicates between them each other. They are not separate systems. They in some part they communicate and use between them. So it's pretty important. We are monitoring also operators monitors the antennas. So any kind of you know temperature troubleshooting or they miscontrol communications with the system, we are always there available to troubleshoot with them. So the antennas are safe, the system is safe, and they can operate normally. Any any problem that has to be investigated is being recorded, and there's a lot of data on JITA as the Atlassian suite, and we use a lot of Atlassian um, applications to document and also communicate with other teams. So when we have an investigation, we create a report, and through there we can communicate with the developer groups of Europe or East Asia. It's really important for our group to use Jira as example.
Yeah, for the
So
people
they,
that doesn't know, Jira is issue tracking technology.
okay, perfect. Is there any application or tool system, I don't know exactly the word for it, that you were really excited to work with when you got to work in ALMA? Like something that blew your mind or
Well,
romance? Or,
it's not like it blew my mind, because I was working with the ACS for a long time, but I have always been passionate about working, using, and developing ACS. I think it's a framework that requires a lot of improvements, and a lot of them have been going through the years. But it's always an impressive thing to have a framework that works with our 66 antennas, with our all our complex subsystems, and it's really impressive to get into the depths of this software and sometimes see some very dumb bugs that are within the software, and then you have this very big beast that does a lot of great job, you know.
yeah. And for you guys, Camilo or Maria Jesus? Maybe for the
For,
people that are watching, maybe electronic engineers that, wow, say, yeah, I want to work with this system or, you know?
for my case was mind blowing when I saw by myself and I have to troubleshoot the the logging, everything that passed through the system or is happening to antenna. You can go to the code and see what is logging, what is happening right now in that second of anything during the system. But it's a lot, like millions of
Very
events
fast.
coming every second, and they're never stopping.
Wow.
If something is missing in a log, something is wrong, because they're alive most of the time. So it's like taking the temperature of a baby when it's alive. I don't know. The system is always alive, so it's always writing something. And when I saw the amount of data we were gathering, and when we have to troubleshoot if something is not going well, it took me a while to understand what is what's what. So we have millisecond of events. So there's a lot of I think going on every fraction of a second.
Yeah, that's amazing. For you, Camilo?
For me, I think it was I think it was the control system, because when I was doing my second internship, I got the possibility to visit the the operation support facility on San Pedro Atacama, and more specifically, I had the possibility to visit the control room of Alma, and the fact that you could move 60, 64, 66 antennas all simultaneously with a push of a button on your mouse.
Yeah, that's really
At that
great.
point, for me, it was part impressive, part like, how do they do it, right?
Yeah.
So it wasn't it wasn't much of a wow moment, but a moment of how do they do it? How do they do it? Moments, right? How
I want to
to
learn about
I
all
want to
this.
learn about it. I want to understand how they do it, how the software works, and also how the data moves from being picked up by the antennas, how the data moves through the system, how it writes to the correlator machines, how it then moves to this pipeline processing that Maria Jesus talked about, and how at the end it gets delivered as a package to the astronomer. Um, that for me was pretty mind blowing. I really didn't knew how it worked, but I really found it fascinating. And then when I got the opportunity to work here at Alma, I also got the chance to learn more about how the system actually works. So
Yeah.
at the end, it ended up giving full circle. So
Mhm.
that's great.
Amazing. Thank you for sharing. So we have some comments on from our viewers. We have greetings from Guatemala. Jose, who says you got this. Franco Bello, regards to all. Asking about the Spanish version of this tour. Yes, we're having at 4:30. A las 4:30 el tour en español. And Jose is asking, how much time do you spend or need to respond to the different scientific requests to set up everything? Who wants to answer that
Well,
question?
I think this is a very complex question because there's a lot of different stuff going on with scientists. I can reply about request gathering. Requirements gathering. So once we have a new feature oncoming, we have to get together with the scientific people here at our observatory, and we have to have several meetings with them to define what actually they want to achieve with this new functionality. And we have to design the solution for what they're asking, and then we have to actually make the implementation. So exactly how much time do we spend doing that? I'd say somewhere around 10 and 20% of our time in the software development area. But I think that Maria Jesus can probably comment on the operation side. How much time do they use or spend with the scientists there?
Software delivery, my experience is update or any new change is delivered every 2 months. So every 2 months, we set up the system and environment to astronomers to test it. Anything that is detected there, we try to notify the teams. But after that part has been delivered from Camilo's team, so everything is normally is completely smooth until the quality assurance from the astronomer. This happens every 2 months, and the astronomers also joins and send requirements to any developer or in case Thomas teams or developers around the world. And when there's some pretty huge change that need to be emergency, like an emergency installation, has to follow up a lot of a process of approval, as the impact of any change on the system without testing it properly can broke a lot of things. So when emergency installation, for example, that has been detected that is blocking some of work with the observatory, our team, the support team, is notified to coordinate the time with the astronomers and also the science group, and we agree on, okay, tomorrow at this time we have the system to install an emergency patch, for example. Everything has to be coordinated between all of us, as antennas are being monitored, the system has to be monitored, and we are all participants of the observatory, not only the software group. We work with the engineers that make maintenance, and also we work with the science group that's in charge of observing and also using the daily, every moment, the system. So this is can be daily reviewed between all of the actors of the observatory.
Okay, great. We have another question. Trevor Nicol. Hi from the UK. The talk was fascinating. How large are the data packages that you deliver to the scientists?
Well, I don't think this is easy to answer either. There are different sizes of packages. It depends on the scientific objective. Usually it goes from a couple of gigabytes up to a couple of 100 gigabytes, maybe half a terabyte or something like that for the bigger ones.
Okay. And he's also asking, how often is the mainframe hardware replaced and updated, or is the original? Or is it the original?
So I can answer that too. It's usually replaced every 5 to 6 years. That's the mainframe or the general purpose computers. But if we go for the more specific pieces of equipment, they are not regularly updated, but rather they go through a project follow-up. You know, you prepare a new project for obsolescence management or of a specific equipment, or for increasing the capabilities, etc., etc. But all the specific stuff developed for ALMA are usually going a different life cycle. But everything that is general purpose goes with this support license for 5 to 6 years, and they have to be updated at the end of that.
Great. And Jose asked us another question. How do you manage the new requests and the daily operation? Is the same team? Is it the same team?
Maybe I can answer this question. There's every week there's a priorities meeting. So every request that is being planned for next week, for example, is being scheduled and time coordinated the week before. If there anything is really, really urgent, we do it in the same moment, like taking the fire extinguisher to turn down a fire. But coordination and planning are really important too, as we have limited resources on the system, and also we have to make efficient use of our time and for example, unplanned problems. Like, I don't know, a funny example of my last shift was energy blackout, and that wasn't planned.
Yeah.
There was energy on the site, and you have to postpone anything you have planned for that day or that week to take care of recovering the system and also the servers and the antennas.
Well, and the last question will be, are there any work positions available in your group now?
Yes, there's one from frontline software support engineer, I think, for our team in the support and diagnostic group. It's open. Maybe they can search on the ALMA posting.
Yeah, on
I
the
think
website. Yeah, on the
yeah.
website. So guys that are watching and are interested, and girls also, you can apply on our websites. So, well, thank you so much for joining us today. It was a great virtual tour that we had, understanding our ALMA software. And we'll be finishing. I don't know if you want to say anything to wrap up the presentation.
Well, I just wanted to say thank you for inviting us, and thank all the people that was watching us.
Yeah. Thank you very much.
Thank you. Thank you, everybody. Have a great day.
Thank you, everyone. Have a great day.